what I've done is I've tried to draw out number 7 and 8, and then I'm going to talk about 10, and I think I can talk about 18 a little bit too, even though it got a bit cut off. So again, a dilation is where something, a shape, well, okay, you have two shapes. One of them is technically called the pre-image, the other one is called the image. You can think of it as like a before and after. So basically you start with a shape and then you look at another shape and you say, could this second shape be like a larger or smaller version of the first shape, by either making it shrink or making it get bigger? Kind of like blowing up a balloon. As you blow it up, generally the shape doesn't change, just the size does. So in number 7, all right, so this MNPQ quadrilateral, you know, is a four-sided shape. MNPQ, those are the corners or the vertices of the quadrilateral. These little apostrophes here on the other one, you say prime, the word prime, so like M prime, P prime, or Q prime, P prime, N prime. Those are the four corners of the other shape. And they use the same letters, so you know they kind of go together, but the little prime mark, the little apostrophe mark, means it's on the other shape. So MNPQ is like your pre-image, that's the before. M prime, N prime, P prime, Q prime, that's like the image or the after. So for number 7, they just want to know, is this one a dilation of that one? So it's basically a yes or no question, and then explain how you know. So one way to tell is to look at all of the sides. Like, let's look at, I do sort of color coordinate this side and this side. You know that 5 is 1/3 the size of 15, or basically you make a fraction out of the image and the pre-image. So this side, the after side, over the before side. 5/15 reduces down to 1/3. Then you're supposed to do that with every pair of sides. So let me color coordinate. This 8 kind of goes with that 24. If you make a fraction out of that, 8 over 24 reduces again down to 1/3. You're supposed to do this with every pair of sides. You can't just do a couple and then make a conclusion, because they trick you by doing not all the sides quite right. So here we got 7 over 21. You can reduce 7 over 21 down to 1/3. So far, all these sides are proportional, but when we get to this last side, this pair of sides here, 4 over 18. Where can I write that down at? I'll write it over here. 4 over 18. When you reduce 4/18, that reduces down to 2/9, which is not a third. See, all of them would have to be the exact same fraction in order for these to be considered dilations. So, since one pair of sides is not 1/3 the size of the other, this one would be a no. So, not all sides are proportional. And proportional basically is what I showed you there. They don't all reduce to the same fraction. So no, not all sides reduce to the same fraction. Not all sides are 1/3 the size of the others. There's a few different ways you could explain it that should probably be good enough. But so you pair up the sides. So that's one way to tell that two shapes are dilations. A second way to tell if they're dilations is by looking at angles. So if every angle in one shape is the same size as every angle in the other shape, like if they pair up, then they're also proportional. You don't need to know anything about the sides necessarily. So, number 8, triangle RST, that's what I drew here, has two angles, 38 and 75. R prime, S prime, T prime has two angles, 38 and 67. So the question is, are they proportional? Well, I hope you remember from geometry that in a triangle, all three angles have to add up to 180. So if you take 75 plus 38, that is 115. Subtract 115 from that 180. You get 70. Ooh, no. Oh, hold on. I'm dumb. All right. Pretend pretend that didn't happen. And yeah, pretend that like you never heard I was a math teacher. 5 plus 8 is 13. Carry the 1. 7 and 3 is 10 plus 1 is... So 113. Subtract that 113 from 180. And you get 67 degrees. That means that this angle right here is 67 degrees. Over here on this other one, if you add 38 plus 67, 7 plus 8 is 15, carry the 1, you get 115. 115, hold on a second, 180 minus 115 is, oh, what am I doing? Boy, I'm just screwing this up. It's 105. I should have used a calculator. You're going to have no confidence in me whatsoever. That's okay. You can just say something really mean about me when I'm not around. That'd be fine. All right, so anyway, 180 minus 105 is 75. I think it's working. Come on. So this angle works out to be 75 degrees. So now if you look at it, those angles are the same. Those two angles are the same. Those two angles are the same. So number 8 is going to be, yes, they are dilations. All angle pairs are equal, or something to that effect. Okay. Number 10. We've got a quadrilateral named MNPQ, kind of like that one up there. It's the same shape but different size as M prime, N prime, P prime, Q prime. That's basically the definition of dilation. Same shape, different size. That's what dilation means. Well, you could read my handwriting. Same shape, different size basically means dilation. This is a yes. And, explain your reasoning. I would just say same shape but different size is essentially the definition of dilation. It's like I said, a shadow on a wall, same shape, different size. Blow up a balloon, the before and after, same shape, different size. Lots of different ways to explain that. Number 18 is a little harder to explain. It'd be a bit easier. Here, I'm going to try to finish the graph paper. Here, hear my dog's barking in the background, I'm sorry. So, okay. This line has a slope up 1 over 3. This has a slope up 2 over 6. 2 over 6 is the same thing as 1 over 3. These lines are both vertical. These lines are both down 1 over 3, down 2 over 6. I know that's getting a little clustered there. Why I'm talking about this is when lines have the same slope, they basically travel at the same angle. So that, in a roundabout way, kind of proves that this angle equals that angle, since these slopes are the same. This angle equals this angle. Again, these two slopes are the same as those two slopes. So we can get the whole angle thing going, where each pair of angles works out to equal each other. Secondly, this side has a length 4, this side has a length 2. So this side is twice as big as that side. If you look at this one, when you go up 2 over 6 as opposed to up 1 over 3, this 2 over 6 basically is double, which means that side is going to be double of that side. Same thing here, this side is going to be double of that side. So triangle C prime, B prime, A prime is the after. CBA is like the before. This triangle is basically half the size. You see if I kind of draw it like that? Half the size of the other one. So yes, these are dilations, and because this side is twice as big as that side, well, actually, I'm kind of saying that backwards, because you got to think of before and after. This side is half as big as that side. The scale factor, SF for scale factor, would be 1/2. Another way to look at it is this point is half the distance to the origin as that point. And this point is half the distance to the origin of that point. All right, I'm kind of rambling and getting into other details and things. But essentially, when they say identify the scale factor, they're telling you that these are dilations. The scale factor, just hone in on sides and divide them. This side is 2, this side is 4, that's 1/2, so that's your scale factor. If it were asked the other way around, if like all the primes were here instead of here, cross those out, then the scale factor would be 2 because this is twice as big. Oops, sorry. This is twice as big as that. So you kind of have to know your before and after to determine the scale factor. So, you know, it's like anything. It just depends on perspective. You could say the green triangle is half as big as the blue one, or the blue one is twice as big as the green one. In this case, it's a half. So, okay, I'm going to go ahead and post this and rewatch it, and then text me back if you have more questions or issues.